All right, so we're talking through these three spots on this graph, the yellow, the green, and the blue, and we want to discuss the value and the limit at each of those spots. What kind of conclusions did you make? Alex? Okay, so here the limit is D and E, and the value is -2 or -1. Cool, I agree with that. Everybody agree? What about at this place, Sean? What would you say is true about the limit here? It is 2. What's true? But what's that value going to be? It is also 2. Good. And then JC, what about at 6 here? What do you say is true about the limit? The limit. What am I approaching from both sides? -1. Good. And then the value down here is going to get me, is that -3? Value is -3. Everybody understand the difference between the two? They're kind of weird, but we got limit, we got values. Only at one of those spots is the limit and the value the same. Agree? This spot right here is the only place where the limit and the value are the same. What is happening at that graph where the limit and the value are the same compared to the other places on our graph where the limit and the value are not the same? That spot is continuous. Remember what continuous means? What did we say? What was the easy definition of continuity that we said before? You don't pick up your pencil. If I were to draw this line, if I were to go from here, I'm going, boop, I didn't have to pick up my pencil. At this spot right here where the limit and the value are not the same, I went here and then I jumped. That's discontinuous. Right here where I have to boop, pick up my pencil, it's discontinuous. In order to be continuous, the value and the limit need to be equal to each other. That's exactly what we're doing today. Let's look at it. Okay, we are talking about continuity. Let's see how that goes. So we are talking through continuity. Again, we just talked about the most basic version of what continuity means. When we talk about being continuous, it means don't pick up your pencil. You're not going to see that in a textbook anywhere, but if you can have that visual image of I don't pick up my pencil, then you know in general what a continuous line is. In order to be continuous, we are going to use a very specific definition for continuity. There are 3 things that have to be true for continuity. All right, 3 things. And we really could talk it 2 different ways, but each way we're going to be continuous. All right, one of the ways we just talked about it. What did we have to have in order to be continuous? We have to have a value. There has to be a closed dot. If there's not a closed dot, then it's not going to be continuous. The other thing we needed to have was we needed to have a limit. You had to approach the same thing from both sides. Not only did you have to have a value and you had to have a limit, but what else needed to be true? They got to be the same. Those are our 3 elements. A value, a limit, and an equal sign. Those 3 things have to be true. You got to have a value, you got to have a limit, they got to be equal. That's how you can prove continuity. That's one way of doing it. And I always used to just teach that, and students got lost as to what you need. So I've changed, and I went to this way instead. When we look at a limit, I'm going to write it in plain language. I'm going to show you in calculus language. In plain language, when we're finding if this spot right here is continuous, what that means is that I go from the left, as I go from the right, and I come from the middle, all 3 of those things need to be the same. Okay, left must be equal to the right, must be equal to the middle. Left, right, and middle. Those 3 things have to be equal. Left and right are going to tell you the limit, and the middle tells you the value. If all 3 of those things are equal, then you're good. In calculus, you can't just write left, middle, and right. Instead, we'd have to write that out, which would be the limit as x approaches. I'm just going to pick a number. I'm going to pick the number 1 from the left of f of x. Has to be equal to the limit as x approaches 1 from the right of f of x. That would need to be equal to f of 1. That's the middle. That is a setup that we have to show. If you do not write limit notation when you're talking about continuity, you will not get points for it. Okay, that's the AP exam. That's how they grade it. You have to show that limit notation. Make sense on how we decide if something is continuous or not. All right, so looking at these problems down below, I really like them because they're describing things pretty well. Go ahead and fill in these three things real quick with your neighbor. Lydia, what did you say the limit was as x approaches 3 from the left? 3. What about limit as we approach 3 from the right? -2. What about the middle? It is also -2 because that's a closed dot. Is this graph continuous at negative or at 3? No, it's definitely not. You can see that pretty clearly here because there's a big old jump in my graph. All right, but we can also see it from here. From this right here, since the limit from the left and the limit from the right are 3 and -2, there's no limit. The limit does not exist. Okay, since the limit does not exist, I don't even need to go to that third one because if the limit doesn't exist, it's not going to be continuous. And the other way we could say is these three things are not the same, so no, it's not continuous. Everybody understand what I'm doing there? Let's go to the next one. Okay, limit as x approaches 2 from the left. Chris, what would you think the limit is as x approaches 2 from the left? It is 2. What about 2 from the right?
2.
It is also 2. 2 from the left, 2 from the right. What about g of 2? That does not exist because there's not a point. Is this graph continuous at 2? No. Again, pretty clearly not continuous because you have to pick up your pencil. But justifying it using calculus, it's that setup right there. The limit from the left is 2, the limit from the right is 2, and the value doesn't exist. And since the value doesn't exist, it's not continuous. One more. We're finding the limit as x approaches -1. So here's -1 right here. We're finding the limit from the left. So Megan, what's the limit from the left going to be? 3. What about the limit from the right? What about the value? It's 3. The limit exists. It's 3. The value exists. It's 3. Is it continuous at -1? Yes, it is continuous. Why? Because this, and this, all three things are equal to each other. That's what we're looking for in order to be continuous. Make sense on how we describe that using calculus. Looking at a picture, easy. Describing using calculus, a little more challenging. That's what we're trying to do. One of the most important things in calculus is being really good at free response. Okay, that is going to be a change for some of you. Some of you will be great at that because you pay attention to details. Some of you are a little bit more scatterbrained and you will not be as good at free response. You're going to have to work at it more. Okay, so you have to understand what's going on. Free response questions are half of your AP exam, and you have to use specific language in order to get full credit. Okay, that's what we're going to talk about. We'll spend next Monday where we do nothing but work on free response questions so you know exactly what you need. Let g be the function defined by this equation right here. G of x is equal to this guy for that one when it's -5 to -3, and that equation from -3 to 5. Is g continuous at -3? We're going to use the definition of continuity in order to explain our answer. So you might have forgotten this. Anybody remember what that shape right there is going to be? It's kind of like a square root, but it's not really a square root. It is actually a semicircle. Okay, that is a semicircle. Think about it. It's x squared plus y squared, but we square rooted it. And it's not plus or minus, it's just plus. That's why I'm only getting the top of the circle. Is that graph from this dot to that dot, is that graph continuous? Yeah, from dot to dot, it's continuous. Not outside of it, but from those two, it's continuous. What about x plus 7? What type of shape is x plus 7? A line. Is a line continuous? Yeah. If this function is continuous, the one thing that has to be true is these two things need to match up. If these two lines touch each other, like that right there, is that new shape continuous? If it's anything but touching each other, is it continuous? That's what we're looking for. That's what we're trying to describe here. All right. And to prove that, we're going to use the definition of continuity. All right. So to use the definition of continuity, we are going to do this. We're going to find the limit. As x approaches, what number do I care about them being continuous at? -3 is the only place we care about. We're going to find the limit as x approaches -3 from the left. I'm going to find the left equation. Which equation up there am I going to use to find the limit as x approaches 3 from the left? The top one. The top one is the left. Those are numbers less than -3. And so I'm going to use that equation right here. I'm just going to write it down. Square root of 25 minus x squared. That's the limit as x approaches 3 from the left. That right there, in order to be continuous, we are trying to decide, is that equal to? Just an equal sign with a question mark. We don't know. We're trying to decide, is it equal to or not? Is that thing equal to the limit? as x approaches negative 3 from the right. Which equation am I plugging into to find the limit from the right? The bottom one, x plus 7. That's the left. That's the right. How would I find the middle? What equation would I plug into to find the middle? The first one. Well, we already know what that's going to be. We can write that down. 25 minus, and it's not just x squared. I really want to plug in negative 3 and square it. Obviously, whatever I get here is going to be the same as that one, but that's just showing the left, the middle, and the right. Everybody with me so far? Find those numbers. See what you get. All right. So we're going to do this a lot in the future. This is the biggest free response thing that we can do in this chapter. How am I going to find this limit, Lily, as x approaches negative 3 from the left? Yeah, plug it in for x. So she's taking the square root of 25 minus negative 3 squared. What did you get when you did that? You get 4. Good. Then we do the next one. Okay? We're trying to decide, is that equal to my next one? Chris, how'd you find the limit on the next one? What'd you get when you plugged in negative 3? Negative 3 plus 7 gets me 4. And obviously, what am I going to get when I do that? 4. We just did the same thing right here, but that's equal to 4. That is my answer, but we're going to go ahead and write that in words. So we want to make sure that we are using the definition of continuity. So we're going to just sum up what we just said. G is continuous at x equals negative 3 because the limit as x approaches negative 3 from the left. And a lot of times students just write the limit. You got to say the limit of what? It's the limit of g of x. There's got to be an equation there. The limit as x approaches negative 3 from the left of g of x is equal to the limit as x approaches negative 3 from the right of g of x is equal to g of 3, negative 3, is equal to 4. They're all 4 of those things are equal. The limit from the left, the limit from the right, the middle. And then what is the number? Oh, it's all equal to 4. That's my answer. Okay? It's putting into words what we said. In order to be continuous, the left, the middle, and the right need to be equal. This is the left, this is the right, that's the middle. All 3 of them are equal to 4. So we have proven using calculus that they're continuous. Is it annoying to write out the limit every time? Yep, but you're going to do it because that's how you score points on the AP exam. Questions on what we did there? Cool. That's the hardest part of the day. Let's go to the next part. 2 types of discontinuities. Okay? 2 categories of discontinuities. Here's what a discontinuity looks like. Okay? There is a jump discontinuity. It's pretty obvious why it's called a jump discontinuity because you jump. You go one line here, you stop, and then you jump up to another one. A jump discontinuity. Another type of discontinuity is called an infinite discontinuity. What do you think is happening right there when you have an infinite discontinuity? There's an asymptote. If there's an asymptote there, they're not going to reach each other because they're going to infinity. That's a discontinuity. The weirdest one is this one, oscillating discontinuity. It might look like they connect, but they don't. It is randomly jumping from point to point. I've never seen them ask it on the AP exam, but if they did and you see that craziness, it's not continuous. Okay? Those 3 types of discontinuities are referred to as non-removable. Those are non-removable discontinuities. It's the subcategory there. Jump, infinite, oscillating. We have another type of discontinuity called a hole discontinuity. It's called a hole discontinuity because there's a hole. All right? It's different than a jump because they're approaching, the limit exists when you have a hole discontinuity. It's just a hole. Okay? If you have a hole discontinuity, if you got a hole, can you fill it up? Boop. If I had a dot right there, is it discontinuous anymore? No, it'd be continuous. So we refer to this as a removable discontinuity because if you got a hole, you could fill it. Okay? You could remove that discontinuity if you just plugged in the hole. Does that make sense? The difference between non-removable and removable. Removable hole, non-removable is any other type. Go to the backside. I gave you a cool little graph right here. Example number 2. Determine all the x values where the graph is not continuous. And for each one, tell me, is it removable or non-removable? Okay, so you're looking through that graph, deciding where is it removable, where does it have non-removable discontinuities. Talk to each other. Go. All right, let's look. Show me with your fingers. At what two spots do you have a removable discontinuity? At what two spots do you have a removable discontinuity? What are you looking for on your graph for a removable discontinuity? A hole. There's a hole right there at 3. There's a hole right there at 5. Removable discontinuities at 3 and 5. Non-removable discontinuities. Show me with your fingers. Where do you have a non-removable discontinuity? That's anywhere that's not just a hole. What kind of discontinuity is it right there at -1? That's a jump because your graph jumps. What kind of discontinuity is it right here at 1? Infinite because you're going towards infinity. Make sense on what we're looking at there? They could also give it to us in an equation. Now, this is a lot more of a pre-calc question. Consider g of x. List the x values where g is not continuous and classify each type of discontinuity. Think about it. Talk with your neighbor. Decide when is that graph not going to be continuous. Go. This is a rational equation. When is a rational equation not going to be continuous? Holes in vertical asymptotes. When the denominator is 0. How can I decide if this thing has a denominator of 0? Factor this guy. We're going to get x plus 8 and x minus 5 on top. And on bottom, we're going to get x minus 5 and x plus 2. What's going to happen in your rational if there's going to be a hole? Numerator and denominator cancel. There's a hole there because if I plugged in 5 on top and bottom, I'd get 0 over 0. And using limits, we know if we get 0 over 0, that's a hole. Okay, so it's removable at x is equal to 5 because there's a hole. What is where's our other one going to be? -2, because what is happening at -2? A vertical asymptote. Make sure you understand the difference between a hole and a vertical asymptote. They could ask those questions. Questions are there. Example 4 says, find a value of k to make f of x continuous at x equals 2. So we're trying to make this thing continuous. We've got some graph and then a value. In order to be continuous, what has to be true about my equation? What two things need to be true? They got to have value. We got to have a limit. What's got to be true about them? Equal. Which equation that's given here am I going to use to find a limit? This guy is finding a limit because if I'm finding a limit, do I care what happens at 2? I'm using that one right there. Okay, so to find the limit, I'm going to find the limit as x approaches 2. And to do that, I'm using this equation right here. That's going to get me a limit. We just did that on our last quiz. That's going to tell me a limit, but I need the limit to be equal to the value. What is going to tell me the value for this problem? It's just k. It's just k because that's what it is when x is equal to 2. So we want the limit to be equal to the value. We just make a little baby equation here. Solve that equation. Figure out what k needs to be. We go to solve it. What happens when I find this limit? I try to plug in 2. What do I get when I plug in 2? 0 over 0, so I got to factor. Then I am going to cancel. And then I'm going to plug back in. Take 2 and plug it in. 2 plus 3 equals 5. And 5 simply is equal to k. If my k is 5, then it's going to be a continuous graph. That 5 is going to fill up my hole that was there in the graph. Okay? Let's try another one. Find another value of k to make f of x continuous. This first equation, x squared minus k, show me with your arms, what does x squared minus k look like? It's a parabola. Are parabolas continuous? Yeah, parabolas are continuous. Your arm didn't like break off and jump somewhere else. What about 4x plus 2k? That's a line because k is just a number. Are lines continuous? Yeah. Okay. They are continuous. Look at this picture real quick. I think it's important to understand what's happening. I've got a parabola when x is less than 5. I've got this line when x is greater than 5. I want to know when they're continuous. Right now, is it continuous? No. Still not continuous. Somewhere in there. We got to keep going. Somewhere in there. We don't know necessarily where it was, but it was somewhere in that spot when those two were continuous. That's what I'm trying to find. So, to figure out when they're continuous, what do I need to look at? In order to be continuous, what has to be true? Limit and the value. This one's a little bit easier because it's different at least. This one I know what the value is. It's going to be when x is equal to 5. I want to know the limit as x approaches 5 from the left, because 5 from the left is going to be this equation. I want to know when is that going to be equal to the limit as x approaches 5 from the right. And that's going to be this equation. When I find the limit as x approaches 5 from the right, that's also telling me the value because it's greater than or equal to 5. Go ahead and solve that thing. Find the limit. Show it to me when you get an answer. All right. Some of you seem very confident. Some of you not so much. We take 5. We plug it in. What are we plugging 5 in for? X. We don't know what k is. That's the whole goal. Is to find k. 5 squared minus k equals 4 times 5. So 20 plus 2k. I'm going to subtract 20. So I get 5 over here. I'm going to add k. So I get 3k. Divide by 3. Divide by 3. K is 5/3. Let's check it. If I make my k value 5/3, are they going to connect? I'm excited. There they are. Is this graph continuous at that spot? Yeah, they're touching each other. They're approaching the same value, and you have a closed dot right there, which is what we were looking for overall. Makes sense. Try the last one. See what you can do. Yeah, good. Yeah, fingers are tough. Yeah, good. We take 3. We want to find the limit as x approaches 3 from the left, and I want to find the limit as x approaches 3 from the right. From the left, I'm using this equation right here, 2x plus 9. I want to know where is that equal to negative 4x plus k? We plug in. You take 3, you plug it in, you get 15. You take 3, you plug it in, it gets you negative 12 plus k. You add 12, you add 12, you get 27 as k. Continuity. In order to be continuous, the limit, the value have to be equal to each other. Limit exists, value exists, they're equal to each other. Or the limit from the left, the limit from the right, and the value are all equal to each other. Whatever way you want to say it is fine. Just make sure you show all 3 parts.